Okay, very brief discussion of the basic graphical characteristic of exponential functions. Okay, the basic function is y equals f of x equals b to the x. The defining graph characteristic is as follows. For some x displacement represented by this arrow, and we'll explain exactly what that means in a second, y doubles whenever x changes by this displacement. So, in order to construct the graph, we pick any point not on the x-axis and start. Now, when I constructed this earlier, this was my starting point. So I applied this x displacement from the x-coordinate of this point, got the x-coordinate of my next point. What do I know about my next point? The y-coordinate has to double. So here's the y-coordinate of this point. Here is double the y-coordinate. We're used to doubling. We know we can do it with compass and straight edge. Very straightforward. So we now have this point on the graph. And then what? Well, we apply the same displacement once more. I don't think I got it quite even, but you get the idea, and you can improve on what I did. You can use a compass and straight edge to construct this graph completely, or at least to construct a series of points which, when correctly connected by a smooth curve, gives you the graph of the general exponential function, the unlabeled, unscaled graph. So we apply that x displacement from here to here, and we know that our y value is going to double. So here's our y value, we double it, we get the y value of this point. Then we do the same thing, same x displacement, double the y value, so we go from here up to here. I don't think I quite doubled it, it should have been a little bit higher, but we still get the idea, and you can always, and you should, construct your own. Matter of fact, I'm going to assign you to construct several. Okay, well, how do we get these points over here? We started here. Now, this is all we had. Well, obviously, if we find the point from which this is our x displacement, if the point to which applying this x displacement gives us this point, then y is going to have to double between here and here. So we just move to the left. We put the arrow down here where it ought to be and find out where we should have started. And then we take half of the y value here. So we cut the y value in half, and then we do the same thing again. We cut that in half again. That gives us a graph that, with certain caveats, can be scaled to represent y equals b to the x for any b. So I'm going to make the outlandish assertion that this graph is exponential if and only if it can be scaled to represent y equals x to the b for any value b. So we could take this graph with any value b and scale it to represent y equals b to the x. Or if we want to do y equals a times b to the x, we can do that too. If you can do this, you can do that. So it's sufficient to say we can do this. Okay? Another characteristic of the graph is exponential. I'm going to claim, and we might or might not be able to prove this, that the graph is exponential if and only if the same x displacement, that is, some consistent x displacement, results in a doubling of y starting from any point on the graph. So this would have to work for every point on the graph. Because we say we could start from any point, that means that we have to be able to start from every point. Otherwise, there would be some point where we couldn't start, and this wouldn't be so anymore. You might think about the logic of that statement. Okay. Well, we can put these two statements together. The graph is exponential if and only if this condition. The graph is exponential if and only if this condition. So we conclude that this condition is true if and only if this condition is true. Now, if and only if, I'm using that kind of in a cavalier manner. We haven't really discussed what we mean by if and only if. It means that the statement and its converse are both true, but you might not know what that means. Basically, it means that to say that the graph is exponential is completely equivalent to saying this, that if the graph is exponential, this has to be true, and if this is true, the graph has to be exponential. Here, graph is exponential if and only if this condition means that if the graph is exponential, this condition has to hold, and if this condition holds, then the graph has to be exponential. Well, I can put those together and say that the green underline here is equivalent to the green underline here. That is, if this condition is so, then this condition must be so, and if this condition is so, then this condition must be so. I can elaborate on that just slightly, although I've probably already confused you. If this is so, well, then the graph is exponential, and if the graph is exponential, this is so. So, if this is so, this is so. Conversely, if this is so, then the graph is exponential. If the graph is exponential, this is so. So if this is so, it follows that this is so. That's worth thinking about, but if it makes you crazy, you can ignore it for right now. Okay, well, our conclusion then is for any value of b, the graph can be scaled to represent b to the x if and only if the doubling condition holds for all x. This is the doubling condition here. I think we understand that, and that's the same as the condition as I've stated it over here. I didn't have room to write the whole thing out, so I just referred to it as the doubling condition, but the doubling condition means this. Okay, so there's kind of not only an introduction, a briefer introduction to exponential functions and the basic graphical characteristic, but a discussion of the logic, of some very important logic that we need to really make the mathematics tight.